So, welcome to Physics 2, Physics 305, Electricity and Magnetism. The official time for the lecture for this class is Monday and Wednesday, 4 to 5:15 p.m. The lab is 2:30 to 3:45 p.m. on Wednesdays. If you guys are okay with it, I was thinking on Wednesdays we could switch the lecture in the lab so that there wouldn't be a gap in between. We could have lecture and then immediately have lab, and then you guys would be free to go after you were done with lab. You okay with that? Okay, I will let Dominica know. I'll send her an email or something. I'll put up an announcement about it anyways. My office hours are Monday and Wednesday, 10 to 11:30, Tuesday and Thursday, 11:30 to 12:45. I'll generally be around. Those are just the blocks I've set as official office hours. You can find me here Monday through Thursday, pretty much all day. So I'm usually in this room or in this hallway. My office is down at the end of the hallway around the corner. It's room 305. So you keep going down to the end of the hallway and turn just left around the corner. Okay, that's that. Let's see. You need a calculator. I'll have calculators you can borrow for tests. For homework, you can obviously use your phone or whatever. Questions from the exams will be drawn from the readings, the same book as you used last semester. And you can work with each other on homework, but you're going to have randomized numbers on your homework. Homework is Pearson. I believe you're going to need a code, though. It should be much like last semester. I'll be happy to help people get on, because for some reason, the way that Pearson works is a huge pain in the ass. I think in general, there is, you have a code either in, I think the code, I believe the code is in the course materials section. Yeah, course materials. That I think is where you can find your access code. I know most of you did this last semester. Don't know if the book thing you got lasts for a year or not, but if you do need help with it, I'll be happy to help. So you should have an access code that you can use. It's in course materials or it's in your bookshelf. But I think it was in course materials last semester, right? It's in course materials then. So it'll be the same as it was last semester, where you have to log in through Blackboard the first time in the homework section. And then it's going to ask for an access for a key. The key is in course materials. And I'll be happy to help you with it if you need it. Schedule. I'm going to start with electric fields and forces. That's chapter 19. We'll move on to talk about electric potential, and then we'll talk about current and resistance and circuits. Then we'll have our first exam on chapters 19 through 21. Then we'll move on to magnetism. We'll talk about magnetic fields and forces post spring break. We'll talk about AC current circuits and electromagnetic waves a little bit. And then we'll talk about optics, wave optics, ray optics, and optical instruments. Hopefully we'll get through all that. Yeah. And then the last exam will be on the last set of chapters. So are there any questions about the schedule? If you have any questions, you can always find me and ask. So starting with chapter 19 on electric charges, forces, and fields. So here are some electric field lines around electric charges to sort of show you the idea of a field. The idea that there's this field permeating through all space generated by electric charges and such. So we'll start by talking about what electric charge is. We'll talk about insulators and conductors. We'll discuss Coulomb's law, which is about the force between electric charges. We'll discuss the electric field, electric field lines, which are a tool for visualizing the electric field. Then we'll talk about shielding and charging by induction and electric flux and Gauss's law. So, electric charge. So, demonstrate electric charge. So the effect of electric charge is first observed as static electricity. If you take certain materials and you rub them on certain other materials, you get what is called I can't remember exactly the term, but you build up static electricity. You build up charge transfers from one object to another, and then there is an electric charge. And you can observe that this electric charge, for example, can attract small pieces of paper, can allow you to do things like stick a balloon to the wall. So after being rubbed on a piece of fur, for example, an amber rod will acquire a charge and can attract small objects. And that's actually where the term electricity comes from. It comes from an old word for amber. And we can also do something similar with a glass rod, and we'll find two amber rods will repel each other, but an amber rod and a glass rod will attract, and two glass rods will attract. So there's some sort of two types of electric charge, and like charges repel and opposite charges attract. And these are conventionally, what you get on an amber rod is a negative charge. What you get on a glass rod is a positive charge. These were decided by, I believe, Benjamin Franklin, and are basically arbitrary and mildly annoying, because it would be convenient if they were the other way around. The signs would be nicer. Because it turns out the electric charge, the primary thing that's moving around, what you do static electricity like this, or in most electrical stuff, is electrons. Electrons are little, they're mobile, they all have the exact same charge, which is expressed with a lowercase e. This is the quanta of charge. It's like the base unit of charge. Electrons have this charge, and protons also have this charge. Electrons are negative, protons are positive. The inconvenient thing about choosing that the way the signs were chosen is that the thing that generally moves around is electrons, and they are negatively charged. So there's a whole bunch of fun stuff where the things that are moving move opposite the direction of the current, for example. There's a bunch of stuff that ends up slightly counterintuitive because of that. It's unfortunate, but it is the way it is. the magnitude of an electron's charge is 1.6 times 10 to the minus 16 coulombs. The coulomb is the SI unit of charge. A coulomb is actually quite a lot of charge. Yeah, it's something around 10 to the 18 electron. 5 times 10 to the 18 electron. So the electrons in an atom are in a cloud surrounding the nucleus, and they're the things that can move around easily. So the reason the thing that carries charge is negatively charged is because it's the electrons, which are on the outside of atoms. So they're the things that can be pulled off and dropped back on. They can move around more easily than the nucleus can, which is where the positive charge is. So when an amber rod is rubbed with fur, some of the electrons in the atoms in the fur get transferred to the amber, leaving the amber rod negatively charged and the fur positively charged. When I rubbed a balloon with my hair, some of the electrons probably from my hair went to the balloon, but I'm not 100% sure on that. I can never remember which way is which for a rubber balloon. But that's what happened. Some of the electrons got transferred one way or the other, and my hair ended up with one charge and the balloon ended up with the opposite charge. And one of the things we find is that the total electric charge of the universe is constant. You cannot create, the electric charge is conserved. So in any interaction, the total amount of charge will not change. Now you can have a positively charged thing and a negatively charged thing interact and destroy each other and end up with something neutral, but the total charge of the universe is conserved. You can't end up with more positive charge out of nowhere, for example. Also, electric charge is quantized in units of E. That charge constant. So that E is 1.6 times 10 to the minus 19 coulombs. So this is sort of the fundamental unit of electric charge. So an atom that loses an electron ends up positively charged. It's now a positive ion. It has a positive charge of plus E. If an atom gains an electron, it ends up negatively charged. It's a negative ion. It has a negative charge of minus E. If you transfer electrons from one atom to another, one ends up positive, the other ends up negative. They end up attracted. This is how you get table salt. Now, some materials can be polarized. They're slightly more positive on one side than the other, and they can rotate to line up with an external charge. And this is how this charged object is being attracted to the neutral form. The charges on this object pull the opposite charge towards them. They attract. The like charge is repelled slightly, and there is an attraction from a charged object to a neutral one. So that's how you can pick up little pieces of paper with a charged rod, things like that. So in an atom of sodium, there are 11 positive charges of magnitude E. So what is the total positive charge for a mole of sodium? 1 mole is Avogadro's number of the object. That's 6.02 times 10 to the 23rd. So the total charge, Q, is going to be the charge per sodium atom, which is 11 times E, because there are 11 positive charges. Each of them is E times Avogadro's number. So 11 times 1.6 times 10 to the minus 19 coulombs times 6.022 times 10 to the 20. The important part of this is the 10 to the 23rd, not that last 10. And if you multiply that out, you get 1.06 times 10 to the 6 coulombs, which is an enormous quantity of charge. That balloon has a tiny fraction of a coulomb. Like 1 coulomb is a lot of charge. So here's a question that's sort of a just think about it question. If you have an amber rub and you rub it with fur, it gains a negative charge. So when I rub an amber rod with fur, it will become negatively charged. Does it gain or lose mass? And what is the charge of the fur? So this doesn't have an answer in the slides because it's just an answer the question thing. So do you think it gains or loses mass when an amber rod becomes negatively charged? Does it gain or lose mass? Yep. It gains electrons, so it gains mass. It's a tiny amount, but it does gain some mass. And then what's the charge of the fur after those electrons move to the amber rod? It's positive. Now, there are certain types of materials. Most materials are insulated. They do not conduct electricity. Some materials are conductor, like metals. These are materials where there are loosely bound electrons that can easily move through the material. They have conduction electrons that are free to move throughout. Most metals are conductors. Other things, other materials are conductors. And then if most materials, the electrons are pretty well bound. So electrons tend not to move from atom to atom. Most non-metals are insulators. So, well, okay, maybe not most materials, because there are a lot of metals out there. But non-metals tend to be insulators, metals tend to be conductors. There's a small category of stuff that's sort of lousy conductors that it's easy to change the conductance of. These are semiconductors. They're incredibly useful because they're sort of in the middle. And it's relatively easy to make them conduct better or conduct worse. And and there are ways to control that, conduct better or conduct worse electronically, which lets you make switches, which lets you do computing. But most materials fall into they're either conductors or insulators. Generally, metals are conductors, non-metals are insulators. There's a few exceptions, like graphite, which is a non-metal conductor. Now, if you have a conductor, like a metal, if there's any excess charge on it, well, that charge can move around. So it will spread out. Because if you throw some extra electrons on a metal ball, those extra electrons don't want to be near each other. They repel each other. So they spread out to distribute over the surface of the conductor. On a sphere, they will be evenly spread out. There are also semiconductors, as I mentioned. They have properties that are intermediate between conductors and insulators, and you can change their properties with their chemical composition. And if you're really clever, you can set up their chemical composition so you can change their chemical composition with electric fields. There are photoconductive materials which become conductors when light shines on them. So you can use those to detect light. Now, remember, in conductors, so if I have a metal container like this, or a metal cylinder, and if I bring a positively charged rod, let's say this balloon was positively charged, I don't know, towards one end of the cylinder, what charge does that end of the cylinder end up with? So this is positively charged. I think I discounted. But if you bring a positively charged rod to one end of a metal cylinder, remember that metals are conductors, charges in them can move. What charge ends up at that end of the metal cylinder? If I bring a positively charged rod up, so let's say this has a positive charge, I'm bringing it up close but not touching it. Remember, the charge within this can move. What happens to negative charges around a positive charge? Yeah, this ends up negatively charged because the negative charges are attracted to it, the positive charges are repelled. And so the end of the cylinder ends up negatively charged. You draw the negative charges to you and push the positive charges away from you. And this allows potentially for something called charging by induction, where you draw the negative charges to one end, you ground the other end, and effectively get rid of the positive charges on the other side, and your whole thing ends up negatively charged. Now, if you have two charges floating around, they will have a force between them. This is Coulomb's law. That force that is described by Coulomb's law. Much like gravity, it's an inverse square force. The force between any two charged objects, this is the law, is a constant, K, times Q1 times Q2 over the radius squared. And this has absolute values because it's just telling you the size of the force. If you want the direction, opposites attract. So if you don't include the absolute values, the sign, if it's negative, is attraction, positive is repulsion. So strictly speaking, if you want to write it as a vector, you can have like an R hat here, because it's in the direction between the two charges. So there's some sign errors. We'll just leave it like this. The signs get confused. The unit is newtons, opposites attract, like charges repel. And K is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. So you get a lot of force for a relatively small amount of charge, because this is a relatively big number. Compare it to the equation for gravity. The constant for gravity is something like times 10 to the minus 11. gravity is much, much weaker than electromagnetism. And the forces are action-reaction forces. You have equal and opposite forces on each object. They're either pushing apart or pulling together. And if there are multiple point charges, like here, you have to add the forces up as vectors. This can be annoying, but it's also what you need to do to figure out the total force. So here, there's 3 charges acting on Q1 here. So Q2 is pushing it this way, Q3 is pushing it this way, Q4 is pushing it this way. If we add up all those vectors, the total points this way. So Coulomb's law here is stated in terms of point charges. But if you do the math and add up all the little bits, it turns out it works the same for any spherically symmetric charge distribution. So if you have a ball of charge, it'll act like a point charge, as long as the distance is measured from the center of the sphere. And this is analogous to the gravitational behavior for spherical mass distributions, where any spherical distribution of mass will act like a point charge in the a point mass in the center of it. And if you have a conducting ball, it's going to evenly distribute the charge over its surface. So it will end up with a spherical distribution. And the spherically symmetric here is that if you rotate it like around spherical, like a ball, the charge distribution doesn't change. So an electron and a proton are separated by a distance d. They're released at rest. And when they collide, are they at the midpoint of the initial separation, closer to the initial position of the proton, or closer to the initial position of the electron? A useful piece of information is that the mass of a proton is approximately 2,000 times the mass of an electron. And I do not have the numbers to hand right now, but that's the important thing you need to know. Protons are much heavier than electrons. So we have an electron and a proton. An electron has a charge of minus E, proton has a charge of plus E. They're separated by some distance d. So we have plus E, E, minus E. They're going to go in and collide somewhere. Is that collision point going to be exactly in between where they started, closer to the initial position of the proton, or closer to the initial position of the electron? They would meet in the middle if they were the same mass. But so they have the same force, because it's an action-reaction pair. But the proton is much more massive than the electron. So the same force on the proton generates less acceleration. So it moves more slowly, so they end up meeting closer to the proton. Same force, heavy thing, the light thing moves further. So here, let's find the electric force between 2 charges of 5 coulombs, separated by 2 meters. We will be talking about microcoulombs a lot when we deal with real things. 5 coulombs is a lot of charge. So, force between two charged particles is K times charge 1 times charge 2 divided by the distance between them squared. So that's 8.99 times 10 to the 9 Newton meters squared per coulomb squared times 5 coulombs times 5 coulombs divided by 2 meters squared. And this is going to be pushing these two charges apart since they're both positive 5 coulombs. And that comes out to 5.6 times 5.62 times 10 to the 10 newtons. It's an enormous force. But here is an actual physical problem. So Niels Bohr, in an effort to better understand the behavior of atomic systems, Niels Bohr put together a very simple model of the hydrogen atom, where he basically assumed the electron was orbiting in a perfect circle around the proton. This is the Bohr model. You imagine the electron to move in circular orbits around a stationary proton. Surprisingly enough, this works to give you certain properties of hydrogen atoms. And the Bohr orbit with the smallest radius, so you can do some quantum mechanics to figure out what allowed orbits are available, is 5.29 times 10 to the minus 11 meters, given that the mass of the electron, you write up these, so our radius is 5.29 times 10 to the minus 11 meters. The mass of the electron is 9.11 times 10 to the minus 31 kilograms. And we want to find the speed of the electron in this orbit and what's the frequency of the electron's orbital motion. So this is an electron moving in a circle. And the centripetal force is going to be mass times speed squared over radius. The frequency will be 2 pi radius divided by the speed. That's just stuff from last semester for circular motion. So, I'll give you a little while to work this out. And the charge of the electron and the proton is both equal. So when you're working out the force. Oh, wait, that's wrong. I wrote the wrong formula down for free. That was the period. Velocity over 2 pi r. So start by looking at, the force is K Q1 Q2 over radius squared. So we can find out what that force is. It's 8.99 times 10 to the 9 meters squared times 1.6 times 10 to the minus 19 coulombs times 1.6 times 10 to the minus 19 coulombs divided by 5.29 times 10 to the minus 11 meters squared. That's absolute value plus E times minus E over the radius squared. And have to fix those animations. That comes out to 8.224 times 10 to the minus 8 meters. Not a lot of force, but these are little things. That force is equal to mass times velocity squared over radius. So velocity squared is force times radius over mass. Velocity squared is going to be 8.224 times 10 to the minus 8 newtons times 5.29 times 10 to the minus 11 meters over 9.11 times 10 to the minus 31 kilograms. So velocity squared is 4.78 times 10 to the 12 meters squared per second squared. velocity ends up being 2.19 times 10 to the 6 meters per second. So it's going a couple million meters per second. That's fast. Then we can look at the frequency. What's the frequency of that electron's orbital motion? Well, period is 2 pi r over velocity. Velocity is 2.19 times 10 to the 6 meters per second. Radius is 5.29 times 10 to the minus 11 meters. So the period is 2 pi times 5.29 times 10 to the minus 11 meters over 2.19 times 10 to the 6 meters per second, or 1.52 times 10 to the minus 16 seconds. So the frequency is going to be 1 over that. So 1 over 1.52 times 10 to the minus 16 seconds is 6.58 times 10 to the 15 hertz. Sorry about writing down the wrong formula for frequency. But, I mean, it was just, I had it upside down. So, electron orbiting proton, orbits at a frequency of 6.58 times 10 to the 15 hertz, roughly. Any questions about that? Okay. So here we have three charges, sorry. We have a charge Q1 that's minus 6.5 microcoulombs at the origin. Here, we have a charge Q2 at minus 2.42 microcoulombs at 1 meter. And we want to find the net force acting on the charge Q3 that's plus 1.4 microcoulombs. That's located at 0.55 meters. So Q3 is attracted to Q1 with a force in the negative direction and attracted to Q2 with force in the positive direction. Yeah. And we're going to add these forces together. And we'll use our Coulomb's force law for this. But force 3.1, because it's an attractive force, but it's pointing in the negative direction, you can think of it as negative. The radius will be 0.55. Force 3.2, you can think of it as positive, but the radius will be 0.45. Because that's 1 minus 0.55. And remember that micro is 10 to the minus 6. So let's work out the forces. Force 3-1 is going to be negative, because it's in the negative x direction. And it's k times q1 times q3 over radius 2, or radius between them squared. So that's negative 8.99 times 10 to the 9 Newton meters squared per coulomb squared, times 6.5 times 10 to the minus 6 coulombs, times 1.4 times 10 to the minus 6 coulombs. Because again, these are micro coulombs, that's 10 to the minus 6, divided by 0.55 meters squared. That will be negative 0.27 newtons. Force 3-2 will be positive, is in the positive x direction, and it's going to be q2 times q3 over the radius between them squared. Remember that that's only 0.45 meters, so it's 8.99 times 10 to the 9 Newton meters squared per coulomb squared times 2.42 times 10 to the minus 6 coulombs times 1.4 times 10 to the minus 6 coulombs over 0.45 meters quantity squared. So force 3-2 is 0.15 newtons. And the total force will just be force 3-1, negative 0.27, plus force 3-2, 0.15, negative 0.27 plus 0.15 is negative 0.12 newtons. So charge 2-3 is minus 1 coulomb. It's on the line segment between charges Q1, that is 3 coulombs, and Q2, that is 4.5 coulombs, which are separated by 1 meter. If Q3 has 0 net force on it, where is it located? So this is about balancing the forces from Q1 and Q2. Q1 has is 3 coulombs and Q2 is 4.5. Sorry about that. So this ends up giving you a quadratic. So remember that force 3-1 in this case will be negative because it's, this negative charge is being pulled towards Q1. And that's going to be minus, and if Q3 is at point X, that'll be minus K times Q1, Q3 over X squared. Because that's the distance from Q1 to, so here, let me draw a picture. This is Q1. This is X. This is Q3. This is Q2. This total length is 1 meter. So this short distance will be X. So this distance here is X, and this is 1 minus X. So we have negative K Q1 Q3 over X squared, and positive K Q2 Q3 over 1 minus X, quantity squared. So if the total is equal to 0, the magnitudes of these two forces have to be equal to each other. So K Q1 Q3 over X squared equals K Q2 to Q3 over 1 minus X squared. The K's will cancel. As will the Q3s. You get Q1 over X squared equals Q2 over 1 minus X squared. Then you can cross multiply. Okay, this is weird. That's not how I would normally do this. Did something weird here. Maybe. That looks like the right solution. But it's this stuff, and I'll work it out how I would normally do this. This is going to be X squared Q1 equals. Oh, I did the square root of both stuff. I see. I did this. Q1 over Q2 equals X squared over 1 minus X quantity squared. Take the square root of both sides. Square root of Q1 over Q2 equals X over 1 minus X. So 1 minus X. Square root of Q1 over Q2 equals X. So if you both divide both sides by square root of Q1 over Q2, you get 1 minus X equals Q2 over Q1 square root of X. I just did the quadratic. You could also just do a quadratic and get the same thing. Let me check what the full. Because clearly I did something weird when I put the slide set of slides together. I'm just gonna check. Okay, so the book, I copied this from the book, which is why it's confusing. Because it's like, take the square root of both sides, rearrange and solve for x. So divide both sides by this, so we have root q1 over root q2 minus root. Minus. Oh, that's not 1 minus plus, that's a minus. Minus. This is plus. The 1 is equal to the square root of q2 over q1 plus 1 times x. X is equal to 1 over 1 plus square root of q2 over q1. Okay. So yes, this does solve to this. There's just, the book skipped a whole bunch of algebra. There's the algebra. And then you can plug in the numbers and get 0.62. You could also leave these as squared and generate a quadratic that you can solve. But you can get away with taking the square root of both sides. That'll be it for today. So I will see you guys on Wednesday at 2:30. I will put up an announcement about the fact that we are switching lecture and lab, so everyone can see, and you should see that announcement soon as I finish writing it. And the lecture is recorded and will be up on Blackboard later tonight. Blackboard just got updated. I just updated to Ultra, so and hopefully Ultra is better. It's going to change again soon, anyways.
Yes, right. Thank you.
I don't know when we're changing to Brightspace, but we are going to be changing to Brightspace at some point. No. No. Not with the chaos of things being reassigned. I don't want to do it.